Welcome back. The topic this week is to wrap up Wix Theorem, which we proved last week. And we're also going to present something which is called Wix Generalized Theorem, which is something where you will find very, very handy. Now, one thing which you probably noticed if you were able to reach one of the last points of the exercise yesterday is that you had a 4-particle state and you were going to calculate the expectation value of the ground state with the Hamiltonian which we had. Now, with 4 particles, this becomes already a little bit cumbersome when you do all the contractions, even with Wix theorem. So we are going to use that case, this exercise, as a way to motivate the particle hole formalism. Because in many cases, what we have is an interaction or an operator which is at most 2 or 3 body. That means that it acts on 2 particles at a time. So if you have a string of 10 creation operators which define a state with 10 particles, you would then have to loop through all the possible contractions with a 2-body operator and 10 particles. But only 2 will be acted upon each time, which means that you're going to have 8 other creation operators for that specific state, which are not acted upon by the operator. Now, redefining your vacuum is something which is going to allow us to actually get away from this many particle expectation values to just expectation values around the Fermi level. So we are going to look at excitations of states below and above. And that's going to simplify a lot, the calculations which we are going to look at. But let me quickly remind you of Wix theorem. And then we need another part of Wix theorem, which is an obvious extension of Wix theorem, which is called Wix Generalized Theorem, which is an extension of Wix theorem to a general product of normal ordered operators. So let's remind ourselves of Wix theorem as a short repetition here. So we have a chain of operators, and I'm not specifying whether these are creation or annihilation operators. I'm just writing them down like this. And this chain of operators, Z to a W, that can be rewritten in terms of a normal order product where all the creation operators are to the left and the annihilation operators are to the right. And when I take the expectation value of this quantity, this is automatically 0. So what you see here, this kind of compact notation means actually that we're computing some kind of transition probability or an expectation value. And then it had the sum over all contractions of the type of 1 pair of operators being contracted. So then we had I'm going to keep this kind of bracket notation for the normal order product. And you will probably notice that different textbooks have different ways of actually setting this up. So we have a sum of all the 1 contractions, and then we have 2 pairs which are being contracted, and the sum of all those. And what we saw is that this contribution here, like the sum of all possible 2-pair contractions, 1-pair contractions, and so on, when we have performed the contractions, that gives us a Kronecker delta, if it's a contraction which gives non-zero. And then we are left with simply a set of operators which get normal ordered, and that means that these expectation values or transition probabilities are automatically 0. So it means that we normally tend to just skip these terms, and then we end up with the final number of pairs where all the terms are contracted. So all pairs of operators are being contracted. And so we have a plus here and plus, and this is simply the sum over all pairs being contracted. And we can only have an even number of creation and annihilation operators. So all the operators are being contracted, and this is marked like this. So that's the only term which survives. And we looked at examples, and one of the examples if you got time to look at it on the Lipkin model, is actually you setting up the expectation value of the ground state, where you have an ansatz for the ground state. Okay, so there's something which is called Wix Generalized Theorem, which is also not so difficult to prove. And this is going to become extremely handy when we are going to look at expectation values of more complicated operators. What Wix Generalized Theorem says is that if you have an arbitrary product of chains of normal ordered operators, then the expectation value of these quantities, they can actually be rewritten as the sum over all the contractions between operators from the different chains, but not within the chain itself. So let me write it down here. So Wix Generalized Theorem, and you will see a demonstration of this immediately. So an arbitrary chain or an arbitrary product of creation and annihilation operators in which the operators are then given as strings of already in normal order form, in which the operators are given in terms of strings of normal ordered operators is given by, so I have a chain of these normal ordered operators. You could now think of a chain A1, A2, up to some A of n. That's one chain. And this is multiplied with another chain of normal ordered operators. And what you're going to see is that basically everything we set up when we calculate expectation values or transition probabilities is actually going to be given in terms of such chains. So we will have a new chain here, B1, B2, up to some B of n. And then we have a new chain here of a C1, C2, up to some C of P. Just to give you an example, this can be given as the normal order product of all these operators, A1, A2, AN, times B1, B2, B of n, times C1, C2, up to C of P, plus, and now I'm going to put a sign where I say all primed, and I have to say what all primed is. And this is a normal product of the operators being contracted not with themselves within a chain of operators, but only between the operators from the different chains. So that means that I can only have chains of operators like this. So this could go to that one, etc., etc. So this is an extremely powerful theorem. It's actually generalizations. So the contractions here run only over contractions between operators from different normal order products. So this all prime, that means that the contractions run only over contractions between operators from different chains and normal ordered products. So the best way to see this is to look at an example. So let's take an example here, and we are now going to calculate an expectation value of a final state, alpha 1, alpha 2, and then we have in this specific case, we take a one-body operator, H0. So we're looking at the operator for the energy of alpha 1, alpha 2. So this is something which we have seen before when we also defined H equal to a sum over alpha beta, and then we have a matrix element H0 beta, and then we have an A alpha, A beta. Now notice one thing here. This operator is actually already in a normal ordered form, right? So this is normal ordered with respect to the true vacuum. So we could actually have written this, but we don't do that. But you could have written that if you want to use a normal ordered notation, alpha, H0, or beta, and then you could have written this as the normal ordered operator A alpha dagger, A beta. So this is actually not the same as when we calculate the expectation value. So normally people would use a slightly different symbol for that. But I hope this is not to be misunderstood. So this is actually an operator which is already normal ordered. So if you then look at this state, alpha 1, alpha 2, this is A alpha 1, A alpha 2 dagger acting on 0. This is also normal ordered, if you look at it. And the same thing when we now look at alpha 1, alpha 2 here, that is the same as 0, A alpha 2, A alpha 1. And this is also normal. You can also see this as a normal ordered operator. So what we are going to have now is a chain of operators which now have been normal ordered. So when we look at this specific expectation value, which we have up here, this one, we could now actually rewrite that in terms of the product of 3 normal ordered sets of operators or strings of operators. So we could actually rewrite this alpha 1, alpha 2 of H0 of alpha 1, alpha 2, and we can rewrite this as an N. And now I'm writing this in a more compact form here. So I would have an A alpha 2. Let me just rewrite it. A alpha 2, A alpha 1. And then I have a normal order product of A alpha dagger, A beta, multiplied with the normal order product of A alpha 1, A alpha 2 here. And then, yeah. Oh, sorry, yeah, now I see that. And then we would then have simply a sum here over these alpha and betas. And we are calculating now a expected value. So this is multiplied with a vacuum state. And then we have this specific matrix elements whose evaluation will depend on the contractions which we make. So if we now look at the contractions, so let's just rewrite this in a simpler way and just look at the contractions. And this is normally what you would see in textbooks, that people tend just to skip all the other quantities and just look at the contractions here. So we have an alpha 1 over an A alpha 2 here. So what we would get then is clearly that we can have this contraction and we can have that contraction. And that means that this contraction here, these are contractions which are non-zero. we know that if we now were to take this contraction here, that's automatically 0. This contraction with the operator itself is 0, right? And we know that this contraction here is also by definition equal to 0. So you see now that the way we have set up the chain of operators, it means actually that if we try to take contractions between these operators here within the same normal order product, that gives us always 0. Does that sound plausible? So that means that the only non-zero contractions are those which link operators with different normal ordered strings of operators. So that means that when you look at the sum of all the contractions, actually Wix Generalized Theorem is a consequence of you having defined the commutation rules and then we have the other contraction here where we also have defined that A alpha dagger, A beta, 0 is equal to 0. And we would rewrite this as an A alpha, A beta contraction here. And that's the same as A alpha dagger, A beta dagger. So that follows from the way we have defined the vacuum and the anti-commutation relations. And when we then look at contractions, it follows that there's only one, which is non-zero. So when we now write out a given state and a given operator, they will always be in a normal ordered form. So when we take expectation values, actually Wix Generalized Theorem follows automatically from the way we have defined the anti-commutation relations. So this is an example of an application of Wix theorem, which makes life easier, because you would think when I have to put up all the contractions, maybe I should run through, let's say, this term, and then, or this term here, or that term there. You don't need to do that. You need only to look at contractions between operators from different normal order strings. So that's something which simplifies life a lot. And that means that when you look at, let's say, the exercises which we have, so if we now take a closer look at another example, so that's the exercise on the Lipkin model. There we had an ansatz for the ground state, which was given by A1 dagger, A2 dagger, A3 dagger, and A4 dagger. So these are specific states which we have. I don't know if you got time to get to that point, and that's why I just bring it up here. So when you now calculate the expectation value of the operators, so suppose now we take the interaction piece without having made the simplifications in the exercise, and we just write this interaction piece in terms of the operators here. So we have an alpha, beta, gamma, delta, and then we have an alpha, beta, V, gamma, delta, and then we have a normal ordered already chain of operators here, delta, A, gamma, like this. Now, when we now look at the expectation value of the ground state ansatz, so remember again that in this Lipkin model, this state phi 0 is a state of your computational basis. It's not the exact eigenstate. You're assuming now that this could be an ansatz for the lowest lying state, but it's not given that it will be the lowest lying state. So let's look at that one. Now, this is going to be proportional to a whole string of operators. So what we are going to have then is a string of operators where we have A4, A3, and this is also normal ordered. And then we have the operator itself. And then I have A1 dagger, A2 dagger, A3 dagger, and A4 dagger. So when you're calculating this now, if you use Wix Generalized Theorem, life is a little bit simpler because now we have 3 chains of normal ordered operators. So it's this chain, it's this chain, and it's this chain. And you see now that if I try to take a contraction here, this is 0, any contractions within the normal ordered string is automatically equal to 0. So the only types of contractions which give you something which is non-zero are those which link the different normal ordered strings. So what I would have now when I look at the contractions, so I would get now, so I'm just setting up now. Suppose now I look at this set of operators here. I have this one with that. And then I can combine these operators here. And you see that the only possibility which I have in addition now is that A3 must go to A3 dagger because 3 is different from 4, right? And same here. Now, if I now keep A3 and A4 fixed and I don't let them be acted upon by the interaction, it means now that I would have in addition 3 more terms here. So let's keep A3 and A4 fixed, and let's only have the interaction acting on A1 and A2. So that means that here I would get a term which links A gamma with A2, and similarly A delta with A1. I can keep this one fixed. So that's one new contribution, which can be non-zero. And then I can continue like this, and I would get a new term where I take this one like that, and I can have this term here, or I can now just keep this term here and link it up with the first one, which is simply A gamma being contracted with A1 and A delta being contracted with A2. So that would be the interaction acting on A1 and A2. And when you sum up then the operation on A1 and A2, so acting on A1 A1 and A2, when I collect all this term, that gives us simply a matrix element, which is going to be given by 1, 2 of V, 1, 2 minus 2, 1 of V, 1, 2. I could have chosen to use an anti-symmetrized matrix element. That's fully possible. I will still get the same result. Now, what you see now is that if you then move on, you have a new pair which you can act upon. So you would repeat with H1 acting on A1 dagger and A3. So instead of having 2, I take 3. And then you would repeat again with H1 acting on A1 and A4, right? So if you look at the contractions now, you shouldn't be surprised to see that 2 is replaced by 3. And then you would repeat again with A2, a new pair, acting on A3. And then you repeat again with A2 acting on, no, the operator acting on A2 and A4. And finally, you would have A3 dagger on A4. So these are the kind of pairs which you can actually act upon. So you should get 6 terms. So that means that when you sum up then, what you will find is that the contribution from this phi 0 of hi of phi 0 is going to be equal to the sum over I less than j, and you're going to have these matrix elements where I and j run from 1 up to 4. And then you're going to have ij of v, ij minus ij of v, and then you have ji here, which is the exchange term. And then you can start looking at the type of interaction which you have. So in the exercise which you have, the interaction acts only on specific terms of the states. So it depends on the spin. So then you can actually take these different terms which we use to decompose the interaction in terms of, and then you can figure out which ones are zero and which are not. So this will be a typical expectation value. And now you can expand the computational basis, and you can actually calculate then using this Slater-Condon rule, which we saw in the previous exercise set. So you can now take a Slater determinant like this and just compute these different transition probabilities, or transition matrix elements is perhaps a better word. And then you can then set up the Hamiltonian matrix. So we are going to live with this Lipkin model for quite some time, because I'm going to reuse it when we do full configuration interaction theory. We're going to reuse it when we do Hartree-Fock theory. So it's a model which has a lot of the many-body physics in it, and at the same time, it's so simple that we can actually hopefully see the wood for the trees. That's the kind of hope, and it's a model which has been used a lot in physics, in particular field like nuclear physics and atomic physics, because many of the interactions there have similar properties as those which we saw in this Lipkin model. Any questions so far? Okay, so these were just two examples on Wix Generalized Theorem, which actually makes life much, much easier when we are setting up the contractions. Because what you will probably, I don't know if you got to that exercise, just seeing all this chain of operators can sometimes be a little bit intimidating, and it doesn't look like an exciting thing to go through all these kind of contractions. Now, there's one thing here, before we move on to the particle hole formalism, where we're now going to redefine our vacuum, which is going to make life easier. And this is a diagrammatic representation of these contractions and the operators. And then you can often portray specific matrix elements just in terms of a figure, a diagram. And that diagram, you can then develop specific rules, and from a diagram, you can extract the analytical expressions which you need to compute or to code. So let's take a look at the diagrammatic representation here. And we are going to bring in further elements when we have gone through the particle hole formalism. And for all of you which are familiar with some quantum field theory, you've probably seen things like Feynman diagrams. And this is actually what we're going to introduce here. And that gives us a very compact way of dealing with many-body terms and many-body physics. Okay, so one of the reasons is that why we introduce a diagrammatic representation, it gives us a more compact way of representing specific contributions to an expectation value, because we can easily get a little bit lost when we have many contractions. So let's bring up some definitions first. So I'm going to define some basic quantities, which I'm going to make a figure of. So a line or a contraction like this of A alpha dagger, which is non-zero. This is something which I'm going to draw like a line. So this is going to have a state alpha and alpha. So if you don't have an arrow on it, that means that this is just a given state where we haven't performed any contraction. So that means that when I look at an operator, I'm not going to put arrows on the operator itself. So a given operator, a sum of alpha and beta H0, just to give you an example here of a one-body operator of A alpha dagger of A beta. This is something which I'm going to represent. So I'm going to represent the operator here with a line and an asterisk. So this represents H0, or the operator, a one-body operator. Then I have a state here, which I label as alpha, as beta, and this state as alpha. I'm going to give you the kind of rules which we're going to use in order to deduce from a diagram the analytical expressions. So when you don't see any arrows on it, it means that no contractions have been made. Then if we take an operator here, like a two-body operator, so let's just write this out like an alpha, beta, gamma, delta, and then we have an alpha of beta, and let's just write this as an O2, which this could be just a two-body operator. It could be the interaction between two particles, or it could be an operator for specific decay, or whatever. And this is A alpha dagger, A beta, A delta, A gamma. And this is going to be represented with a dotted line here. So that's the interaction itself. And it has two so-called vertices. So this has only one vertex, because this is a one-body operator. And you have a state here, which is given by alpha, and this is beta, and this is gamma, and this is delta. So you could now think, if you want to add time to this, which is pretty natural in many-body physics, you could think of time as something which moves upward. So you could now think of, if you look at the first one, you could have a particle beta coming in, a particle in a state beta. Then it interacts with something. And then after the interaction, which takes place here at a given time, it leaves the system in a state alpha. So this is one of the ways you can actually read these specific matrix elements here. So there are some additional rules here. So you can think of, and I'm just going to write time in quotation mark here, time moves upwards. You will also see these diagrams being tilted, and that means that time moves sideways if you want to introduce time. So you could think of now the state, the bra state, that is typically over the operator line. And we would have a typical operator line like this. This is a one-body operator. And something like this is a two-body operator. And then we have a state which comes in here. And this is what we would say that this is below the operator line. So let me just look up my cheat sheet here and see if I have remembered everything I wanted to say here. Okay. That one. So there are some rules which we are going to set up here. But when you now look at the specific, let's now look at a specific example, which we have seen before. So one of the things which we actually did calculate was this specific matrix elements. We had an alpha 1, alpha 2, and then we have a matrix element for the operator where we had this V operator, and then we calculated beta 1, or let's just write it as an HI. of beta 1 and beta 2 here. Now, when we used Wix theorem, or as we did in the very beginning of the semester, where we actually wrote out a two-particle Slater determinant and went through all the gymnastics in coordinate space, what we found when we did these calculations is, and it depends a little bit on the type of operations which we did, we got a factor of a half when we run through the contractions. So we got an alpha 1, alpha 2 of V. So I'm just repeating what we saw when we did either the calculations in second quantization or in the standard first quantization. And then we got a matrix element where we had an alpha 2, alpha 1 of V, and then we had a beta 1, beta 2. We got another minus 1, and we had an alpha 1, alpha 2 of V, and then we had a beta 2 and beta 1. And then we had the final one, which was an alpha 2, alpha 1 of V, of beta 2, of beta 1. So this is something which we now have calculated many, many times, actually. And we could then use the symmetries. So if we took this matrix element here, if we interchange two particles, we could then show that by changing the indices that this matrix element and this matrix elements are the same. And this matrix element here is the same as this matrix element here, as long as we had this both translational invariance and this permutation symmetry. Okay, so what we can do now is to think of this in the following way. So when we are setting up this in a diagrammatic form, this is the analytical form. If we think of this diagrammatically, so what we have is the following. So we have a outgoing state, which contains alpha 1 and alpha 2. So that means I have now, if I write this as a diagram, I have alpha 1 here. And remember now that I haven't specified any arrow because I haven't done the contractions. So when I put arrows on it, it means that I have performed contractions. So these states, they can be states above the Fermi level or below the Fermi level or whatever kind of states. Then the next thing is that we have now the interaction. So we have this alpha, beta, gamma, delta. And then we have this matrix element, alpha, beta, V, gamma, and delta. And this is then multiplied with A alpha, A beta. So this is the analytical expression which we have of A gamma. Diagrammatically, what we have now is this piece here. So we put labels on the different states, and then we have a gamma and a delta. And now we perform contractions. And so we also have to multiply it with the state here, which is now the incoming state, where we have a beta 1 and a beta 2 here. So if we think of the contractions which we had, we can now have the following contraction. So let me just write it down for you. So we have an A beta 2, A beta 1. So you see that a little bit, it takes always some time to actually get used to the diagrammatic representation. And that's why I'm repeating some of these basic elements which led to the final expression. So if we take this contraction here, oh no, wait, I messed it up here, sorry. I interchanged alpha 1 and alpha 2 with beta 1 and beta 2 here. So this should actually be A alpha 2, A alpha 1, and then I have A beta 1 and A beta 2 here. So if we take that contraction, you see now that we can link this one with that. So that's a contraction. Then I would have this specific contraction here. So I would link beta 2 with delta. And then I can take alpha 1 with alpha and alpha 2 with beta. So that gives me this contraction here and this contraction here. So the diagrammatic thing is, you just look at the diagram and you see now when you have this expression here, sometimes it's easy to get lost. When you write it out in a diagrammatic representation, you can now just bind together different legs. So bringing together alpha and alpha 1 is a contraction. Beta and alpha 2 is another contraction. So that if I do this contraction here, what I end up with then is the following. So I have the interaction. And now I can put in the sign for the contraction. So what I had here was A alpha. If we now look at it, I have an A alpha, which is now being contracted with A. So this is an A dagger. And then I have an A alpha 1. So this contraction here, so that leads simply to alpha 1. The other one is a beta with alpha 2. So that leads to a label alpha 2 here. And then I perform the new contraction. And this case gives me beta 1. And this gives me beta 2 here. Now we could look at the contraction where we take, so let's look at the next one, and we take A alpha 2, A alpha 1, A alpha, A beta dagger, A delta, A gamma, A beta 1, A beta 2 here. So what we could do now, instead of having the contraction with alpha 1 and alpha, we could now simply take alpha 1 with beta and alpha 2 with alpha, and we could still just keep this set here. Now, if you now look at the contractions which we would have to do, we would now contract beta with alpha 1 and alpha with alpha 2. So diagrammatically, the way we actually write this is as follows. So we would now have still the same vertex. So beta 1 comes in here. So we have put a label vector here, or an arrow. But then, since we now are moving to the slot alpha 1, and we are interchanging alpha 1 and alpha 2, what we would have then is a crossing line here. So this contraction. So this gives me now beta with alpha 1. So this is my alpha 1 slot. And this is my alpha 2 slot here. So I'm leaving them in the same place in the diagram, but the way I'm going to read this is a little bit different. So when I'm reading the matrix element, when I want to read out the analytical expression, so this is going to, when you look at this one, this is going to read, when we now put in the matrix element, so I have beta 1 and beta 2. So this is left. This is the right element in the diagram. This is this incoming state. Now, what I have to be a little bit careful with now is, since I have interchanged alpha 1 and alpha 2, I actually have, when you now look at the diagram here, I actually, since this is alpha 2 is the one which is to the left here, and alpha 1 is here, this becomes alpha 2 and alpha 1. So it's the one which leaves to the left out of the vertex. If I go back to this term, this would now read alpha 1, this is the left, alpha 2, which is the right, and then I have V, and then I have beta 1, beta 2. So you would then have left out, and you have right out, and you have left in, and this would be left, sorry, right. I still have to learn the difference between right and left here. Right? Right in for this specific state. And we would have the same in here. So that would be now the left out. And this will be the right out. Now, when you write it like a diagram, you don't put minus signs or plus signs. But when you have interchanged two of these lines, that gives rise to a minus sign analytically. So when I want to read off the diagram here, if I have crossing lines, that means that I just have a minus sign here. Okay, I went a little bit over time, so let me put things on pause the record. So what we see now, when we bring everything together, if we look at the different terms, we are going to get another exchange term. And then finally, we are going to get a term which is the same as the first term. So that means this term here. And that's going to have two crossing lines. So we saw from the calculations here that this gives a crossing line on top. It's pretty obvious to see that this is going to give us a crossing line at the bottom. And this is going to give us two crossing lines. So every crossing line means that we actually have interchanged two fermion operators in order to perform a contraction. So it's a very nice way to indicate that we are dealing with fermion operators and actually have contractions which we need to keep in mind here. So we would get, when we now look at this element which we call minus alpha 1, alpha 2, but where we have the interchange at the incoming level, this is something which we diagrammatically then would write as follows. So we've had the two outgoing lines as before. So this is the left outgoing and this is the right outgoing. Clearly, if you have a free body operator, then with a free body operator, there would be another dot here. You would have another vertex line. And then with the other dot here, you would have another line coming out here. So the kind of way of reading it is that you read from the left to the right. And then, since we now interchanged beta 1 and beta 2, this would be written like this. So we would still have beta 1 coming in and beta 2 coming in, but then they interchange at the positions at the vertices. They get contracted with just the interchanged creation operators. And diagrammatically, we simply write it like this. And then finally, we would have the matrix element, which went like alpha 2, alpha 1 of V, of beta 2, of beta 1. And we have made an ordering where we have alpha 1, or the slot alpha 1 is here. So we have alpha 1 and alpha 2, and then we have a beta 1 and beta 2 here. But now we have to interchange the lines. So we have crossing lines like this, and similarly here. Now it's common to rewrite this. So this would, if we now sum up all these diagrams, we would have a factor of a half. So it's common to actually sum up all these contributions just in terms of two diagrams, one which represents a direct term. So I would have a beta 1 coming in, a beta 2 coming out, coming in, and then similar an alpha 1 coming out and an alpha 2 coming out. And then we will simply write plus, but when we write down the analytical expression, we have to look at the number of crossing fermion lines. So this would simply be written like this. And when we read it, we have to write down the matrix elements, alpha 1, alpha 2, V, beta 1, beta 2 here, and then a minus. And then we have an alpha 2, alpha 1, of V, of beta 1, of beta 2 here. Then it's pretty common to rewrite these diagrams just in terms of 1, and you will often see this one written out in terms of a dot here, something like this, and then you would have lines getting out, alpha 1, alpha 2, and beta 1 and beta 2. So this is often called a Hugenholz notation, or just a Hugenholz diagram. And these are normally called Feynman diagrams. And no, I think Feynman is written with only one n here. And since we are dealing with many-body physics, non-relativistic many-body physics, you will often see them being labeled as Feynman-Goldstone diagrams. That's another type of labeling which you will see in the literature, because Feynman developed everything from quantum field theory and quantum electrodynamics. And then people in the 1950s and 1960s developed a parallel alternative to Feynman diagrams for non-relativistic quantum mechanics. And that's the main focus of this course, actually, non-relativistic quantum mechanics. And the notation is pretty similar. We will have time-dependent theories, time-independent theories, and we're also going to introduce antiparticles, but antiparticles in our case are going to be so-called states below the Fermi level, and they are normally called whole states. So we're not going to deal with real antiparticles. Okay, let's look at another example, and then we move on to a slightly more complicated case, which is more related to the exercises which we're dealing with. So let's now take the one-body operator. So we have a one-body operator, which I'm just calling O1, and this is a sum over alpha beta, and it has a matrix element of O1 beta, and then we have the A alpha dagger of A beta, like this. And then when we're now calculating the transition probabilities or expectation values or whatever we are interested in, then we have a state. Suppose we still stay with this state, alpha 1, alpha 2, and then O1, and then we have a beta 1 and a beta 2 here. So let's stay with that specific example. And we know that when we did the calculations either in first quantization and second quantization, and we went through all the contractions, we saw that we got only the one-body contributions. And we can make life simpler. We can assume that the beta states and the alpha states are eigenbases, form an eigenbasis of the operator O1, or we just can leave it as it stands. Now, if we now take the operator themselves, so what we have, we need to perform the contractions of A2, actually alpha 2, A alpha 2, alpha 1, and then we have an A alpha, A beta, and then we have an A beta 1 dagger, and then an A beta 2 dagger. So let's look at the possible contractions which we can have. So since this is a one-body operator, they can act like this, or they can act on that one. So these are strings of normal ordered operators. And that means that in this specific case, we need to have delta alpha 2 or beta 2 here. So if we now want to write down the diagram, we would start with the outgoing state, which now has alpha 1 and alpha 2 here. And then we have a beta 1 coming in and a beta 2. We haven't put on arrows here. And this is then multiplied with an operator, which now looks like this. And this has a state beta, and there's a state alpha here. So the first contraction which we did is actually this contraction here. and then we made the contraction with beta and beta 1, like that. And then what we have is this contraction here. Now, normally that is just skipped because that's just 1. So we would typically write this just in terms of the matrix elements of the operator, because the other one gives us just a Kronecker delta. So what we would get then would be something which looks like this. I would have a beta 1, and then I would have an alpha 1 here. And then what I would have when we want to write it out, this is going to be a matrix element which is given by alpha 1, O1 multiplied with beta 1. So that would be one of the possibilities. Now, you see now that what we could do, if we look at the operator, and now we have not assumed that the single particle states are eigenstates of the operator. So that means that we need to take into account all possibilities here. So what we could have now, so let's just rewrite it. So we would have an A alpha 2, A alpha 1, A alpha dagger, A beta, and then A beta 1 dagger, and A beta 2 dagger. So if we look at this one, in the previous case, we kept beta with beta 1. So let's still do that. But now we could let alpha 2 go to alpha. But then we have actually alpha 1 to beta 2. So that's also non-zero. If alpha 1 is equal to beta 2, then it's non-zero. So if I write down the analytical expression, this would now give us a minus, and then I would have an alpha 2 here, and I would have an H or an O1, the operator, the one body operator, and I would have a beta 1, and then I would have the Kronecker delta of delta alpha 1 with beta 2 here. So diagrammatically now, if I'm thinking of this as a two-body state, we could still actually write it like that. If it's only a one-body state, you would leave it. But normally people tend to skip the line which comes in here. So this would be a state where we now have a beta 1, and now beta 2 here, and beta 2 here. And that is equal to alpha 2 and equal to alpha 2 here. Now, if you look at this diagram, what we would have, we still have the operator coming in and out. So we have a beta here and then the alpha. And now we have the outgoing states. So this is alpha 1 and alpha 2 here. And then I would have a beta 1 and a beta 2 here. So in this specific case, we now perform the contraction with that one. But then we are contracting this state, alpha, with alpha 2 here. So if we now keep this in terms of a two-body expectation value or transition probability, we would actually rewrite this in the following way. So we would have the operator coming in. So we have a beta 1 here. But then what we would have would be a line which goes like this. So we would have this one going up to an alpha 2 here. But then we have beta 2 coming in, and that crosses line with alpha 1 here. So we have to be a little bit careful when we calculate a contribution like this. And keep in mind that I have assumed that the basis which we have, the single particle basis, is not an eigenbasis of O1. If it had been an eigenbasis of O1, this matrix element would have been 0. Okay? So if I'm looking at an operator like the kinetic energy plus the external potential, where the basis is an eigenbasis of that specific operator, then this specific element which you see here would have been 0. So for this specific case, we would actually draw the diagram like that because this is now a two-body state. So some people tend to leave it out, but then you lose the context. So if it's only a one-body state to a one-body state, then you would never have the bystanding line or the spectator line, as it's called, or the non-interacting line. But since you have two states coming in and two states leaving, then you need actually to take into account this crossing here, because else you would get the wrong expression and the analytical expression when you write out the analytical expression from the diagram. So in this case, we have a crossing fermion line. So you would then simply rewrite it if you want to write the analytical expression. So this would be a minus due to the crossing fermion line. And we would have the operator, which would now be an alpha 2 of O1, and then a beta 1. And this is multiplied with a delta beta 2 of alpha 1. This is the way you would read off this one. So every line or every contraction which is not linked with a matrix element or with an interaction or an operator, you would always write them just as plain lines which go through everything, and these correspond to just a Kronecker delta. Yeah.
Wouldn't it be the same? Should we have a delta in the first one if you scroll up? The first.
Yes. So you have a delta alpha 1. No, sorry. So here you would actually have to multiply this one with a delta of beta 2 of alpha 2 here. But sometimes when you look into textbooks, you will see that people skip it. But it's not correct to skip it because you're actually dealing with a two-body state. And you see the pattern here. When you move on to the other terms, you will actually get, if you now look at this, you will get two more terms. So if you look at the contractions, so let's show that. We would have an A alpha 2, alpha 1, A alpha, A beta, and then an A beta 1 dagger, A beta 2 dagger. So you have now the possibility of having this contraction here, and then you could have this one, and then you would have this contraction. So when you look at that one, what you get then is a term where you have now the incoming states, beta 1 and beta 2. You have the operator here. Of beta alpha. And you have the two outgoing states, alpha 1 and alpha 2 here. And in this case, what you have is that beta 2 is contracted with beta. That's a contraction. And then you have alpha with that one. And that means that alpha 1 is now contracted with that one. And this becomes simply, since there are no crossing lines, in this case, you have two crossing lines, that gives a plus sign. So you get simply a delta alpha 1, beta 1, multiplied with beta alpha 2 of O1 of beta 2 coming in here. So for the case where you have a operator which does not have these states as eigenbases, we will need to account for all the four possible combinations. And this is what you would get if you did the contractions as well. So the final one would be an A alpha 2 alpha 1, A alpha, A beta 1 dagger, A beta 2 dagger. But where we now contract beta with beta 2, and then we would have a beta 1, but now with this one, and then we would have that one. And that would be the last term which we get. I just leave that as a small exercise to you guys to actually look at that. So let's now go back to the Lipkin model, which we have in the exercises. And now you're going to see why it may be interesting to actually think a little bit differently when it comes to the way we are writing up our contractions and the reference state. So in that case, we defined a state, phi 0, which was given by an A1, A2 dagger, A3 dagger, and A4, acting on the vacuum state. And then we have a two-body interaction. So let's now go back and look at this specific term here. So we have a HI phi 0. So this is just the expectation value, and this is a two-body interaction. So let's look at the specific terms which we get. So we will have the outgoing lines. So we have a 1, 2, 3, and 4. And then multiply with the vacuum state. And then we have down here, we have the same. 1, 2, 3, and 4, acting on the vacuum state. And then in between here, we have now a matrix element, or the operator, multiplied with the matrix element. So we have an alpha, beta of gamma and delta. And then we start doing contractions. So one of the things we did then was simply to contract this leg with that one, and this leg here with this state. So you see now, you can actually draw contractions by looking at diagrams. And then you have this leg being contracted with that, and this leg here being contracted with that one. So when I write it out here, what I get is a matrix element 1, 2 of V, 1, 2. And then I have a Kronecker delta of delta 3, 3, and delta 4, 4. So the states are different, right? So that means that I need to make this contraction here, and I also need to make, and let's mark this with red here, and this contraction here. So this gives rise to the Kronecker deltas. But you see now, what you see here is actually that the formalism here starts getting, or the drawing of the contraction starts getting a little bit, how to say, unwieldy. I mean, you're getting many, many different contributions, and it's easy to get lost because the interaction acts only on 2 at a time. If you add more particles, if you have 10 particles, you would actually have only 2 of them which interacts with the interaction, and then you would have the remaining ones which give rise to Kronecker deltas. So can we simplify this? You see this, that this quickly becomes a little bit cumbersome, right? So the question now is, can we simplify this? And since I'm asking this question, it obviously means yes. And that leads to what's called a redefinition of the vacuum state of the vacuum state to a new vacuum state, which I'm going to call for C. C is going to stand for core. So you will have a core of single particle states which are filled, and then you will have states above that which are empty, and that's going to define the Fermi level. And this leads to what's normally called the particle hole formalism. So what that means is that I'm going to define this C. If you now look at the Lipkin model, this could now be given by the state phi 0. So the typical assumption, if you're dealing with fermions, it's natural to think of you having a Fermi level which gets filled up by particles in all the single particle states. So for fermions, we can use the Fermi level to define an ansatz for the state C. So let's go back to what we had in the very beginning. You can now think of you having many such states. And then we have the Fermi level here. And then we have states below the Fermi level. And all these single particle states are filled up with the particles. And this goes up to the final one here. And this will now define our new reference state. So this will be C, or what we normally call the Slater determinant for the ground state, or the ansatz for the ground state. So often, if you have such a system where you have often a well-separated gap between the lowest lying field state and the first excited single particle state, then this begs naturally for this kind of ordering of the single particle states and then the definition of a new vacuum state. So this is what we're going to look at now. And that means also that if you now look at a state, which suppose now that we have a state where we have all the states below the Fermi level, and then we have a specific state below the Fermi level, a state I, which is now empty. So that means that all these are filled, except this one. And this state is a state where we have knocked out the single particle and knocked it up into a state which we can call for A here. So the way you would define this Slater determinant in second quantization, that would be us acting on the vacuum state, phi 0. So that removes a particle from the vacuum state, right? But then I would create a particle in the state A here. So I'm just introducing the kind of notation which we are going to use a little bit later and throughout the rest of the course here. So this gives a compact notation where you will typically see the Slater determinant being labeled like an I and A here. So remember again that the type of interactions which we have, they act on, if we have a two-body interaction, it acts at two particles at the most, at the same time. So what we could define in addition now is a new state. So let's just bring back all these states which we have here. And now we have a Fermi level, and we have a state I here and a state J, which have been left empty. So we have filled in all states here. And then we have a state A here and a state B, which now are filled with particles. So this would be, if I now want to write down the answers for this, I would have an AJ, AI, acting on phi 0. And then I have an A dagger. So I create two particles in these states, A and B. And this is something which we will write in a more compact notation, like an IJ and AB here. And then you can continue like that. You can have three particles being promoted from below the Fermi level to above the Fermi level, and so forth. So the kind of notation which we are going to use now is that this is going to be called a one particle, one hole excitation. One hole state, or one hole excitate, one particle, one hole state excitation. And it's typically just written out as a 1p, 1h. This other state which you see here is obviously a two particle, two hole state. And then you can continue like this and build up all kinds of excitations. So if you have n particles, so with n particles, we can make up to n particle, n hole excitations. or n-particle n-hole states. So if you have an n-particle n-hole excitation or n-particle n-hole state, that means that there is nothing below the Fermi level, and you have filled in n particles in different n-particle slots above the Fermi level. So this is all kind of language which we are bringing in. But the thing which we need to do a little bit now is actually to go through this particle hole formalism, because that's going to redefine our operators. So if you look at the one-body operator, that's going to be redefined now in terms of a new vacuum contribution, which is non-zero. And that's going to be a constant. And that will, so what we're going to see now when we have done all this is and we're going to do the derivations, but let me just anticipate that. So redefinition of operators. So we are going to, at the end, so this is the end product. So we are going to have a one-body operator, H0, which is going to be given by PQ, and we have matrix elements of H0 of Q, and then I'm going to have an AP dagger. But before we come here, we actually need to make a transformation to the particle hole formalism and then redefine things. So this PQ are all types of orbits, below or above Fermi level of single particle orbits. So let me put that in parentheses. And this is going to have, in addition, a term here, which is a constant. So this is just going to run over the states below the Fermi level. So F is now the Fermi level. And I'm going to use a notation for I, J, K, L. These are states which are below the Fermi level. And this is simply going to be given by this term here. And I have assumed now that the basis is an eigenbasis of these states. Now I can then rewrite. So I'm just giving you the expressions, and then now we have to derive them. So I can rewrite this one in terms of a sum, P, Q, and then S, T. And there's a generic matrix element. So P, Q, S, T, they can run over all the single particle states we have. P, Q of V, S of T. And this has a creation operator, another creation operator, and then a T here and an S. And it's going to have an addition here where we now run over P and Q. But then there is a state I here where I is below the Fermi level. So it's going to have an operator of the one body type of AQ, but then it has a matrix element of P of I, of V, of Q of I. So we are going to use anti-symmetrized matrix elements. So this is going to have an AS here. And then it's going to have a constant term, which is the one we have calculated before. And now I'm just running freely. So this has an IJ of V of IJ, anti-symmetrized. So it has both the direct and the exchange term. So if you now think of what we have done till now, so let me highlight two of the terms. So if we highlight this term here, and we highlight this term here, these two terms, they define what's normally called the reference energy, E reference. Reference because I have a reference vacuum state. So if my vacuum state is phi 0, or in terms of this C, which I defined, this is actually the result which I would get in terms of this specific expectation values. So this is normally called the reference energy. Or the vacuum energy, because we have redefined the vacuum. And this is going to be equal to the sum over I less than Fermi. So this is actually a sum which goes below the Fermi level. And then I'm going to have this diagonal contribution of I plus this term 1/2 over sum over ij less than F. And then I have this anti-symmetrized matrix element. So I just wanted to give you the result we are getting to. And then what we have to do now is actually to derive it. But the thing is that when we now are looking at contributions to the total energy, we will often redefine that in terms of something which is called the correlation energy. Because the reference energy is something you can calculate immediately. And if you have a good agreement with experiment and the reference energy, that means that the basis you have chosen is a pretty good one. If not, we actually have to labor more and bring in more complicated types of many-body contributions. So that means that there will be other states than phi 0 which contribute to the energy. So remember also that phi 0 is our computational basis. It's not the true eigenstate of the Hamiltonian. But this kind of splitting up in terms of reference energy and what comes on top of that is something which is widely used in many-body physics, and it's used as a kind of indication of whether your reference state is a good one or bad one. If the experimental energy differs a lot from your reference energy, that clearly means that you need to work a little bit more. So what I've done now is simply to give you the answer, and now we have to actually show that this is the case. So with that, the only thing which we need to do now is to bring up the final definition of the single particle states and the labeling which we're going to use. So we have this set of single particle states above and below the Fermi level. So the states, a generic state without specifying, is going to be given by P, Q, ST, etc. And normally, since we're dealing with at most free body interactions, we're not going to need more than 6 letters. And that's why we have this kind of strange division. So the states here, they typically take labels A, B, C, D. But again, since we at most, in most many-body theories, we deal with at most free particle interactions, then typically we can actually live with just 6 letters, A, B, C, D, E, F. And similarly here, we're going to have the letters A, I, J, K, L, etc. So this is just definitions which we're going to use. Okay, I see we are getting towards the hour, and I thought we could just stop here before we now actually go to the particle hole formalism itself.